This begins E555 with Dr. Zahid. It's Tuesday, April 15th, 2014.
Very much. Excuse me. Good morning, everybody. Let's continue our discussion from last time. We started talking about the architectures of optical networks, and we went, first of all, through the reasons that the trend is toward using optical technologies to support a very high bandwidth. A huge bandwidth is roughly between 50 to 100 terabits per second. Tera means what? 10 to the 12 bits per second. A huge amount of bandwidth. The optical fiber, again, support low signal attenuation, roughly around 0.2 dB per kilometer. Every 1 kilometer span of fiber, the signal will experience roughly about what? 0.2 dB, which is a relatively small attenuation. And that results in we need less number of regenerators over the long haul distances. Over long distances, we'll use less number of regenerators. We'll talk about regenerators in just a second. Optical transmission over optical fiber is immune to electromagnetic interference. Radio signals in the vicinity have no effect on the on the optical transmission. Highly secure. It's very hard to tap into the fiber. The fiber sometimes will break, and the transmission will be what? Will be discontinued. Highly secure. Low signal distortions, again, suitable for carrying digital information. Low power requirements, lighter weight, less space it takes, non-flammable, safe, and more cost-effective. Now, let me just make one comment about the cost-effective. I'm not talking about a fiber, an optical fiber, cheaper than a what? A wire, telephone wire. I'm talking about what? If you compare the same capacity, if you compare the same bandwidth of fiber with an equivalent number of telephone line that have the same bandwidth as the fiber, the cost is what? The cost is you cannot compare the two. You will need a huge number of what? Huge number of twisted pair wires to give you the same capacity as a what? As a single fiber. Clear? So the cost effectiveness, we are talking about what? Comparison with the same amount of what? Band. A typical optical transmission system, I think this is where we run out of time. The optical transmission system, a typical optical transmission system consists of the following. We have an information source. This is not part of the optical stuff. This is not part of the optical stuff. This is an information source generating what? A whole bunch of what? Zeros and ones. Clear? So this one is like a host. Information source generating what? Generating zeros and ones. This is a what? An optical source. For example, a laser, or a what? A light emitting diode. LED stands for what? Light emitting diode. This is a laser or a light emitting diode. We call it what? An optical source. A light signal. This is the modulator. The information will be modulated onto the light signals. Will be modulated into the light signal. And you are going to be transmitting over the optical fiber. When you see a link and then you see a circle like this, this means what? These are optical fibers, Along the way, you are going to have what? An amplifier, an optical amplifier / a what? Regenerator. An optical amplifier is going to amplify the signal. When you hear the word optical amplifier, it means what? It means that it's going to do the amplification in the optical domain. Most of the time, as we will see, and currently, what we have is a what? We have the regeneration. The regeneration is done in the electrical domain. And the hope is that everything is going to be done in the what? In the optical domain soon. It goes through another fiber, and again, as I told you, we don't need that many of these because the attenuation per kilometer is very small. But we need them anyway. We need them along the way. At the receiver, we have what? We have an optical detector, like, for example, a diode, an optical diode or a transistor. Okay, and the signal here, the signal which is an optical signal, when it what? When it falls into the optical diode or the photodiode or the phototransistor, it will convert it back to an electrical signal. Clear? An electrical signal. Now the details of this, by the way, the details of each of the above component, you will study it if you take this course in EE 558. EE 558. And EE 558 is offered every semester. So when I say every semester, it does not include of course, the summer. So it's offered in the fall and it's offered in the spring. What we are going to be interested in this course, in our course, is from a networking point of view. From a networking point of view, rather than what? From an optical point of view or communications point of view. Clear? As you will see shortly. The fiber can come in a what? In a single mode or a multi-mode fiber. A mode means a path. When you say a mode, a single mode means what? A single path. Now, the fiber consists of what? Three components: the core, the cladding, and the jacket. The core and the cladding and the jacket. Most important part, of course, is the what? Is the core. That's where the light signal will be what? Will be traveling. In a single mode, the light signal will travel or will propagate in one path. At one path. So you are not going to get what? Multiple versions of the signal. You are not going to get multiple versions of the signal. Why? Because this one here is so thin. The core is so thin. It's 10 micrometer. Whereas in a multi-mode, you can see that the core is what? Is a wider core. The core is a wider core. And the signal will experience what? Refraction from what? From the cladding. From the cladding. So it goes this way. Gets refracted here, refracted here, refracted here, and so on and so forth. In this example, how many paths do you have? We have 3 paths. You have the what? The direct path, and you do have what? 2 refracted paths. Clear? Okay. Now, in this case, what you are going to be suffering, you are going to be suffering or results in what? In the pulse. If you take the sum of these, you will see that the pulse will become a little bit what? Smeared. It becomes what? Spread. Clear? In other words, and instead of the pulse like this, and instead of the pulse like this, it will become what? Like this a little bit. It gets what? Stretched. Clear? It gets stretched. It gets attenuated. Because of what? Because of this multipath. And this multipath results in what is known as intersymbol interference. Intersymbol interference means what? One symbol is going to interfere with what? With next symbols, with the next symbol, and so on and so forth. The reason is why is that because they are going to come at different delays. This one here will travel faster than this one here. Why? Because this one will go through what? A longer path. That intersymbol interference will have an impact on how much data rate can be supported. The data rate will be reduced a little bit, and the impact will be worsened with the distance. Distance means what? The longer the fiber is, the worse the situation this one becomes. Clear? Okay. This one, of course, is what? Is cheaper than this one. This one is a much better quality than this one. Clear? Okay. Now, then we saw that they did some experimentation to see what is the best wavelength. What is the best wavelength? Remember, by the way, the wavelength is lambda is equal to what? C over what? F. F is a frequency and C is the speed of light. So they did some experimentations and they ended up with a result look like this. And what do you notice? You notice that the best wavelength appeared at what? At lambda equal to what? 1550 nanometer. 50 nanometer. And they found that the attenuation at this value is roughly what? 0.2 dB per what? Per kilometer. 0.2 dB per kilometer. Another medium here, or another minimum here, and this one locally, if you look at the local minimum, appeared at what? At 1300 nanometer, and at 1300 nanometer, they found out that the attenuation is roughly what? 0.5 dB per kilometer, which is what? Which is higher than this one. Clear? So they decided, again, as I told you, they decided to build the grid, the standard grid, or the global grid of wavelengths around what? 1550 nanometer. Let me show you so that you understand what I'm talking about. This is the standard, the ITU. ITU stands for what? The International Telecommunications Union. This is an international group, subsidiary of the United Nations. Subsidiary of the United Nations. ITU, the International Telecommunication Union, built this grid of what? Wavelength. And you can see that the center of the grid is around what? Is around this one, which is what? 1552.52. This is the wavelength is what? In nanometer. So these are what? If you look, by the way, if you look at the difference between this one and this one, this one and this one, you can see that everyone is separated by roughly how much? By 0.8. Separation, or the spacing between the channels is what? It's 0.8 nanometer. 0.8 nanometer. Now, if you translate this in frequencies, you will end up with what? 100 gigahertz, which means what? The difference between the, if you change this one into the frequency, and if you change this one into frequency, you will see that the separation between them is around what? Around 100 gigahertz. Then they decided to make it a little bit what? A little bit denser. A little bit denser. The spacing, instead of what? The spacing, instead of the between them is 100 gigahertz. They defined what? A 50 gigahertz spacing and a what? 25 gigahertz spacing. What does that mean? It means supporting more what? More wavelength. More wavelength. If they get what? Closer and closer to each other, it means what? You are supporting what? You are supporting more wavelength. Clear? That's a denser grid. We'll talk about this in just a second. Clear? Oh, now, the first thing that we need to understand, which is part of the networking issues, which is what is referred to as what? Wavelength division multiplexing. I want you to think about this the same way as you thought about FDM. FDM stands for what? Frequency division multiplexing. A wavelength division multiplexing is the same as what? Frequency division multiplexing. Why? Because I just told you, lambda is equal to what? C over what? F. So different wavelengths, it means what? Different frequencies. The reason they call it a wavelength division multiplexing is that because you are operating in the optical range. What is the purpose, or what is the idea about wavelength division multiplexing? In a wavelength division multiplexing, we have a single fiber. And instead of having what? A single wavelength propagating over that fiber, you are going to have multiple wavelengths. So for example, in here, how many wavelengths do we have? We have lambda 1, we have lambda 2, and we do have lambda 3. This is, again, this is only for illustration purposes. We don't have what? We don't have these pipes. Do you understand or not? We don't have these pipes. We only have the optical fiber. But this is just to indicate to you that each one of these lambda 1, lambda 2, lambda 3 is referred to as a what? As a channel. So in this case, what do we say? We say the optical fiber is supporting how many channels? 3 channels. Each one is on a certain what? Wavelength. On each wavelength, you are going to modulate the traffic. Like I showed you a moment ago. You are going to modulate the information. The information could be from different technologies, from different protocols. So for example, when you see Ethernet, what does it mean? Ethernet over what? Over a wavelength. The data, the traffic, Ethernet frame over what? Over an optical wavelength. Clear? This one, IP or MPLS over what? Over lambda 2. This one, STMN. STMN is what we refer to as what? The synchronous digital hierarchy. Or STS in the case of SONET. SONET over what? Over a wavelength. Clear? So the point that I'm trying to make here is what? Is that multiple information signals modulate optical signals at different wavelengths or different colors. The resulting signals are then combined and transmitted simultaneously over the same what? Over the same excuse me, over the same fiber. Clear? This modulation and this modulation and this modulation has nothing to do with each other. These are all different what? Different protocols. This is the IP, this is the Ethernet, this is SONET, or SDH. Every wavelength is what? Modulated independently of the other one. Physically, you are going to what? You are going to modulate, sorry, you are going to mix or multiplex all of these wavelengths on a single fiber. So you have something like this. Let me show it to you so that you understand what I'm talking about. This is, we call it what? I'll get back to it in just a second. We call it an N-channel point-to-point wavelength division multiplexing. Point-to-point means what? This is one point, and this is what? Another point. We have a single optical fiber. You can see the circle here. This is a single optical fiber. How many what? How many? These are transmitters. This is what? Lambda 1, lambda 2, lambda 3, all the way to what? Lambda n. You are going to multiplex all of them over a single what? Over a single fiber. We say what? We do have a single fiber supporting how many channels? N channels. Each one is on a certain wavelength. Clear? When you hear the word dense wave, DWDM, DWDM stands for what? Dense wave division multiplexing. Dense wave division multiplexing. Here, the number of wavelengths is usually greater than what? 20. Usually greater than 20, which means what? More than 20 wavelengths over a single fiber. Again, as I told you last time, currently they are experimenting with what? 160 wavelengths. 160 wavelengths over a what? A single fiber. Clear? Now, anything above 20 regarded as what? As DWDM. Coarse wavelength division multiplexing, anywhere between what? 4 to 8. We say what? We say coarse wavelength division multiplexing. Clear? Clear? Okay. Now, throughout the course, our discussion, I will always use the word what? DWDM, dense wavelength division multiplexing, rather than what? Rather than coarse wavelength division multiplexing. Clear? Okay. Notice, by the way, just like any multiplexer, like a TDM or a what? FDM, it comes in pair. If this is a multiplexer, this is a what? A demultiplexer. How many inputs does this one have? It has n inputs. How many output? It has one output. In here, how many inputs does it have? One input, and how many outputs do we have? We have n outputs. Clear? So just like any other multiplexer, it comes in pair. Okay. Now, the other device that we will be interested, we are looking at the devices right now. The other device is what is known as a regenerator. Another name, or what they call the regenerator, they call it what? The optical 3R generators. What is the 3R means? 3R means what? It has functionality, 3 functionalities. All of them starts with the letter what? R. The first one is what? Re-amplify. Re-amplify means what? Along the way, you are going to what? You are going to amplify the signal, re-amplify it.
The time is 20 o'clock.
Reshape it means what? Means if there's a distortion in the shape of the pulse, you reshape it to become what? A clean one. To become a clean one, like this. And then what? Retime it. Retime it means what? If there is a timing offset, if there is a timing offset as the signal propagates over the optical fiber, you what? You reset the timer. You reset the what? You get rid of the what? The offset of the timing. Clear the timing offset. You try to what? Correct that offset. Clear? So they call it what? Re-amplify, reshape, and retiming. The issue is what? Is to try to do all of this in which domain? In the optical domain. Currently, again, as I told you, what they do is what? They take what? They have transponder box. They use a transponder box. In the transponder box, what do they have? O/E. What is O/E stands for? An optical signal coming in will be converted to what? Electrical signal. It will be what? Regenerated, reshaped, retimed in which domain? In the digital domain, in the electrical domain. Are you following me on that? And then what? Change it back to what? Optical. E/what? O. This whole thing, they refer to it as a what? As a transponder, OEO. OEO stands for what? Optical, electronic, optical. Optical or electrical if you want. Optical. Electrical and what? Optical. Clear? The idea or the goal is to what? Is to remove this one. To do everything in the what? In the optical domain. everything is in the optical domain rather than converting back to what? Electrical and then what? And then back to optical. Now, of course, there are many products right now in the market that do the what? Everything is in the optical domain. However, it's not yet widely deployed. It's not yet widely deployed. It takes some time for it to be what? Standardized and what? And deployed on a wide fashion. Currently, most of them are done this way. Clear? Clear? Okay, good. Now, so what do we have is the following. Look, what do we have? This is, if you think about it as a what? As a DMUX in here, the transponders are a significant fraction of the what? Of the WDM network. Why? Let's see. It comes in here, lambda 1, lambda 4, lambda 1 all the way to lambda 4 wavelengths. It gets demultiplexed, lambda 1, lambda 2, lambda 3, lambda 4, and there is a transponder for every what? For every wavelength. There is a transponder for every wavelength. Now in here, what happens in here? What happens in here is that you are going to re-amplify it, you are going to what? Reshape it, you are going to what? Retime it, and then what? Convert it back to optical, and then what? Multiplex them again on this side. Lambda 1, lambda 2, lambda 3, lambda 4. So one transponder is required for what? For wavelength, per direction, at a regeneration what? Site. So for every wavelength, you need a transponder. For every wavelength, you need a transponder, and in every direction. So in other words, if you do have two directions, you would need a transponder in one direction, and you need a transponder into what? Into another direction. Clear? When you have an amplifier, remember, an amplifier is a one-way device. One-way device means what? Means you apply the input from one port, you get the output from what? Another port. You cannot apply the input from what? From the other port. You follow me or not? The amplifier, anybody of you have an amplifier, you know that the input and the output cannot be what? Interchanged. Cannot be interchanged. Clear? So you need each one. You need each one of these in each direction if you have what? If you do have the... If you do have both ways or two-way fibers in here. Okay. Now, let's continue with the devices before we get to the networking topologies. The first one is called a splitter. And the other one, we call it a what? A combiner. And the splitter and the combiner. Again, all of these, you will also study it in 558, but not to the detail that we will go through. Because these are part of what? Part of the networking. What is a passive splitter? First of all, whenever you hear the word passive, what does it mean? It means that there is no optical to electrical conversion. There is no optical to electrical conversion. If there is conversion, we call it a what? An active device. This is a what? This is a passive device. So what we have in here is the following. We are having a lambda 1 coming in here on a single fiber. It goes to a splitter. The splitter will split the power. So, for example, if this is P, this one will be what? P1, this one will be what? P2. And P1 plus P2 is equal to what? P. Did you get this or not? Split the power. The power does not have to be split 50-50, but most of the time it is split 50-50. Clear? Notice, by the way, when I say split 50-50, because this splitter is what? Is 1 to 2. We could also have a splitter 1 to what? 4, which means what? Each one will get how much power? 25% of power. Clear? Now, this is, look at this. If this one is carrying information, the same information is going to come here and what? Here. Do you understand that or not? It's the same information, but the power is what? Reduced a little bit. We call it a what? A passive splitter. A passive splitter divide the optical signal on one fiber to 2 or more fibers. These are what? 2 fibers in here, coming here in a single fiber. Most common is what? Is 50-50. Now, in here, what do I have? I have a passive combiner. In a passive combiner, I have what? Again, passive means what? No optical to electrical conversion. Keep that in mind. Now, in here, the combiner will combine what? Will combine 2 wavelengths. This is lambda 1 on a single fiber. This is lambda 2 over a second fiber, and he will combine them to get what? Lambda 1 plus what? Plus lambda 2. Clear? Clear? Okay. Now, when you do this, first of all, remember, as I told you a moment ago, if this is the power P, If you split it 50-50, there is a what? P over 2 and P over 2. Which means what? In here you have lost what? Half of the power. This is also what? Half of the power. Half the power will go in here. Half of the power will go there. Other losses include what? When you put the splitter or the combiner, losses include what is known as a return loss if there is reflection, or the insertion loss, which is what? Which is the power lost from what? From an input to an output. So this one, when you say 50-50, this is just theoretical. Clear? In reality, there will be some what? There will be some power losses due to the insertion of the component. Every time you put a component, you get what? You get some losses. Okay. Now, let's look at a passive coupler and a broadcaster. A passive coupler, again, one more time. When we say passive, what does it mean? There is no conversion to electrical domain. Everything is done in what? In the optical domain. A passive coupler and a broadcaster. I want you to see this. This one in what? What do I have here? Can you tell me what do I have here? I have a back-to-back combiner followed by what? A splitter. Did you get my point or not? Yes? What do I have here? I have lambda 1, I have lambda 2. I'm going to combine them internally. And then what am I going to do? I'm going to split them. So this one here is what? Lambda 1, lambda 2. What am I generating? Lambda 1 plus lambda 2, lambda 1 plus lambda 2. This is a 4x4 broadcaster. I want you to tell me why they call it a broadcaster. Look what we have. Lambda 1, lambda 2, lambda 3, lambda 4. What am I getting at the output? Lambda 1 plus lambda 2 plus lambda 3, lambda 4. How many of them? 4 of them. Why? What happened? When you go here, 4, what is inside? Inside you have a what? A combiner. You are combining 4 wavelengths. Yeah. Let me ask a question. Could this one be lambda 1 and this one could be lambda 1? This one, lambda 1 and lambda 1. Could it be? You didn't understand my question. Listen to my question. These are what? Lambda 1, lambda 2, lambda 3, lambda 4. Could this one be lambda 1, lambda 1? Or there will be collision? Could this one be lambda 1 and lambda 1? Let's see it here. Lambda 1. Could this one be lambda 1? It cannot be lambda 1. Why? Because if this is lambda 1 and this lambda 1, what will happen? They will collide with each other. The information will be destroyed. Did you get it or not? The information will be destroyed. The information modulating this wavelength has nothing to do with the information that is modulating what? This wavelength. Can you transmit 2 frequencies? Can you transmit 2 frequencies, exactly the same frequency at the same time, each carrying different information? Each carrying different information. Can you transmit at the same time? What will happen? If you transmit at the same time, what will happen? They will collide with each other because they are what? They are at the same frequency. That's the same thing in here. This is, remember, a lambda is a frequency. Lambda is equal to what? C over what? F. So when we say different wave, when we say the same wavelength, what does it mean? It's the same frequency. Did you get this or not? All of these wavelengths are what? Are different. If they are the same, there will be what? A collision. Clear? So what do I have here? Lambda 1, lambda 2, lambda 3, lambda 4. What is at the beginning? At the beginning of the broadcaster or a coupler, you do have what? A combiner. You are going to combine these wavelengths, lambda 1, lambda 2, lambda 3, lambda 4, and then you are going to split them into how many ways? Into 4 ways. So each one will get what? Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4, but each one of how much power? Each one is of the 1/4 of the power. Clear? Do you understand why they call it a broadcaster? Do you understand why do they call it a broadcaster? Is this the same? Is this the same signal? They are the same signal. Each one consists of how many wavelengths? 4 wavelengths. Lambda 1, lambda 2, lambda 3, lambda 4. This is also known as a what? As a passive star. Why do they call it a passive star? Let's see if you remember. You remember the hub? You remember the hub or the star? So if this one is sending something, what will happen? The hub will send the same information to what? To all of them. Are you following me or not? This one here, same information in all of them. Clear? These are the inputs. Now, it distributes the power from any input port equally to all the output ports. Collision occur if two or more inputs with the same what? Wavelength are launched. One more time. Go back to the hub. If I have, remember the hub from 450? If I have A here and I have B here, can they transmit at the same time or there will be collision? There will be collision. Here, if they transmit, if they are using the same wavelength, there will be a what? There will be a collision. Clear? Clear? Oh, this is what is known as a star coupler. Star coupler is very important in the architecture of optical network. A lot of devices are referred to as a what? As a star coupler, as we will see in just a second. Clear so far? Clear so far? Okay, good. Now, this is an example of a 4x1 mux using a 4x1 coupler. A 4x1 mux, I want to design a 4x1 mux using a what? A 4x1 coupler. Now, what do I have here? These are the input ports. Input port, input port, input port, input port, port. What am I doing here? What am I doing here? I'm combining, and then what? I'm splitting. I am combining, and then what? I'm splitting. Then I take this one, and then what? I'm combining, and then what? I'm splitting. Did you get this or not? So in this case here, you could end up with what? You could end up with 4 inputs with how many outputs? With what is this? This is at lambda 1, lambda 2, lambda 3, lambda 4. What is this one? Tell me what is this one? This one. Lambda 1 plus lambda 2. What is this one? Lambda 1 plus lambda 2, but at what? Half power. Lambda 1 plus lambda 2. Lambda 3, lambda 4. What is this? Lambda 3 plus lambda 4. Get split. Lambda 3 plus lambda 4. So what do I have here? Lambda 1 plus lambda 2. Lambda 1, lambda 3 plus lambda 4. Get combined to get what? Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4. And then what? Get split. Did you get this or not? Did you get this or not? So if you take the output in here, what do you have? How many wavelengths do you have here? 4 wavelengths. Are you following me? Not 4 wavelengths on a single output. That's why it is behaving as a what? As a 4x1 mux. We were able to design a 4x1 mux using only a what? Couplers. Did you get my point or not? Yes? Okay, good. This is another example of a what? Of a demultiplexer using a what? Using splitter plus what? Optical bandpass filters. OPBF stands for what? Optical bandpass filter. Let's understand what this one is coming. This one is what? It's a 1x4 demux, which means what? The input is coming from here, carrying what? All the wavelengths. So this one is what? Lambda 1 plus lambda 2 plus lambda 3 plus lambda 4. It gets what? It gets, first of all, it gets combined in here, of course, and then what? It gets split. This one combined, get what? Split. Then what do I have? In each one of them, I'm going to put a what? I'm going to put a filter centered at what? At a certain wavelength. So in here, how many wavelengths are coming here? How many wavelengths are coming here? We are going to have what? Multiple wavelengths, but the output will only be what? A single wavelength. Which one of them? It will be lambda 1. Why? Because this one is a filter that will only, a filter is a device that will select what? A certain frequency. Clear? This one will select lambda 1, this one will select lambda 2, and so on. Clear? So what am I building here? A demux. Remember, a demux is what? From one input, how many outputs am I generating? I'm generating 4 outputs. Clear? Okay, good. Now, a passive wavelength router. Let's understand what this is all about. A passive wavelength router. A passive router can separate, again, when we talk about passive, what does it mean? There is no change, there is no transformation to what? To the electrical domain. Everything is done in the what? In the optical domain. What is a passive router? A passive router can separately route each of several wavelengths incident on a single input fiber to the same wavelength on a separate output fiber. We need to have a what? A routing matrix, which I will show in just a second. And the routing matrix is what? Is fixed. What does that mean? Look at what it means. This is lambda 1, lambda 2, all the way to what? Lambda n. This is lambda 1, lambda 2, all the way to lambda n. Lambda 1, lambda 2, all the way to lambda n. Did you get this or not? Okay, now answer first of all the question for me. Is this lambda 1 the same as this lambda 1? Yes, it is. But the information in here, the information being modulated on this lambda 1, does it have anything to do with this modulation? It has nothing to do with this. These are different what? Different devices. What is this one is doing? What is this one is doing? This one is separating the lambda 1, the lambda 2, all the way to lambda n. What is the lambda 1 will go? The lambda 1 will come in here. The lambda 2 will come in here. Why? Could this one be a lambda 1? Could this here, this, do you see this lambda 1? Could it go to here? This one, we are going to have a problem. Are you following me or not? We are going to have a problem in this case. Did you get my point or not? So in this case here, a passive wavelength router, he is generating what? He is generating all the wavelengths, separating the lambda 1, lambda 2, all of it. The lambda 1 will come in here. The lambda 2 will come to the second one. The lambda n will go to the third one. This one is what? Lambda 2, lambda 1, lambda 2, lambda n, and so on and so forth. This one, and this one, and this one. Clear? And then what happens to here? What happens to here is that they get multiplexed. Clear? Now, let me ask a question. Let's see if you can help me here. This lambda 1, in this diagram, this lambda 1, is it the same as this lambda 1? Yes, it is. But could it be this one? Why not? In other words, could this lambda 1 be taken here? Instead of going here, could the lambda 1 comes in here and this lambda 1 goes in here? That's why we call it a router. Do you follow me or not? What is this routing matrix? A routing matrix will tell you what? This connectivity. Not sure you are getting this point. Are you getting this point? Okay, not sure. I want you one more time. Let's try it one more time. This lambda 1, in this diagram, where is it headed to? It is headed to here. Yes? Could it head to here? And instead of going here, could it come here? And this lambda 1, could it go here? Huh? What do you mean? No, you are not getting the point here. Let's concentrate, please. How many times do I need to repeat this? These inputs, you see this input here? How many inputs does it have? N inputs. Every input needs to have a what? A different wavelength. Because you are going to what? Multiplex them. Did you understand that or not? In other words, a lambda 1 here, this one cannot be what? Lambda 1. Why? Because if this one is lambda 1 and this one is lambda 1, you are not going to be able to what? Combine them. They are carrying different what? Information. Did you get my point? But this lambda 1, could it go here? This lambda 1, and instead of going this way, could it go this way? It could go this way. Now, what goes instead of it? In a place of it, what goes? The lambda 1 could go in here. This lambda 1, do you see this lambda 1? This lambda 1 could go in here. This one could come in here. Did you get this or not? It all depends on what? The routing matrix. Where do I want to route this lambda 1? Do I want to route it to this? Or do I want to route it to this? Do I want to route it to that interface? And so on and so on. Where is the router? Can you show me where is the router? The router is this whole thing. This is the router. Here. How many inputs does the router has? N inputs. By the way, when I say N inputs means what? Means the input fiber N, input fiber 2, input fiber 1. Are you following me or not? Yes or no? How many inputs does it have? It has N inputs. How many output interfaces does it have? It has N output interfaces. Are you following me or not? On each input, how many wavelengths do I have? N wavelengths. In each output, how many wavelengths do I have? N wavelengths. However, these wavelengths, are they necessarily the same as this? Of course not. Look at lambda 2. Is this lambda 2 the same as this lambda 2? Where is the lambda 2 went? This lambda 2 went here. And which lambda 2 is this? Lambda 2 came from here. Did you get my point or not? Could this lambda 2 come from here? It could come from here. This is what I mean by a what? A routing matrix. This is the routing matrix in here. And it will determine what? Where is this wavelength headed to? Where is this wavelength headed to? And so on and so forth. But you cannot have the same what? You cannot have the same wavelength on what? On going into the what? Into this output. Why? Because this one will not be able to what? To combine them. This one is a combiner. You are going to combine them. Did you get my point or not? You are going to combine them. This one cannot be lambda 1 and this one is lambda 1. And then there will be collision. Clear? Okay. This is what is known as a what? As a passive wavelength router. A passive wavelength router. The wavelengths incident of the input fiber to the same wavelength on a separate output fiber. To the same wavelengths on a separate output fiber. We need a routing matrix. And the routing matrix is what? Is fixed. Once you decide on a routing matrix, this routing matrix is what? Is fixed. Now, can you explain to me this? Can route n square simultaneous connections? Where did the n square came from? Where did the n square came from? Can you tell me where did it come from? How many inputs do we have? How many outputs do we have? N output. How many combinations can we have? N square combinations. This one could go to either this or this or this or this. The second one could go either this, 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 and so on, so on. Clear? And then we can have what? We can have n square simultaneous connections. Clear the passive wavelength router? Okay. Now, optical switches. Again, this is switching in the optical format. We have two types of switches. We have a bar state, or we do have a what? A cross state. A bar state means what? Means this one is going to be switched to this. This one is going to be switched to this. The cross are what? Are not allowed. The crosses are not allowed. Whereas this one is what? The crosses are what? Are allowed. The straight is not allowed. We call it a what? A cross state. And the whole switch, we call it a what? A 2x2 switch. Clear? This is exactly what we studied earlier in the semester when we were talking about the switching technologies. The difference is that this one is done in the what? In the optical domain, whereas the other one, we looked at it in the what? In the electrical domain. If you look, do you remember these types of networks? We studied earlier the switching architecture that consists of what? For example, the Banaz switch. Are you following me or not? The Banaz switch and so on and so forth. All of this consists of what? 2x2, 2x2, 2x2. And you build the switch accordingly. You notice, by the way, the connectivity in here might not be the same as the connectivity in here, might not be the same as the connectivity in here, and so on, so on. This is a what? A 16x16 switch. 16x16 optical switch. How many inputs does it have? 16 inputs. How many outputs does it have? 16 output. But it is implemented by using 56 2x2. 56. 56, how many units do we have? 1, 2, 3, 4, 5, 6, 7, 8. And how many columns? 7 columns. So we are using 56 switches. Each one of them is what? Is 2x2 in a what? In a Banaz network type arrangement. Just like we studied earlier in the semester. But this one now is done in the what? In the optical domain. You try to build your 16x16 switches using what? Smaller switching elements. The smallest switching element is a what? Is a 2x2, which is what? Which is what I showed you in here. And the state, either a what? A bar state or a what? A cross state. Cross state or a bar state. Clear? Okay, good. Okay, now, active wavelength router or a switch. Let's understand what this means. Listen to this. Let's see if you can help me with this. This is an active wavelength router / what? Switch. What are the wavelengths? I want you to compare this with this. I want you to compare these two together. I want you to compare these two together. What do I have here? Lambda 1, lambda 2, lambda n. Yes? Okay, this one generate what? Lambda 1 all the way to lambda n. So far is the same. Lambda 1 all the way to what? Lambda n. But in here, what am I going to have? I'm going to have switches in the middle. Each one at a certain what? Wavelength. Which means what? This one only switches what? Lambda 1. This one only switches lambda m. Clear? So what do I have? If this is only switches lambda 1, I'm going to take the lambda 1 from here, the lambda 1 from here, the lambda 1 from here, the lambda 1 from here. Did you get my point or not? And then what do? I switches the what? The lambda ones. The one lambda one can go this way. Another lambda one can go that way. A third lambda one can go this way. This is a switch. It's not a combiner. Are all of them entering the inputs to this? The inputs to this, are they all lambda ones? They are all lambda ones. Do they carry different information? They carry different information, but this one is not going to what? Combine them. It is only going to what? To switch them. Did you get this or not? Switch them. One of them will come here, the other one will come here, and so on and so forth. When it comes to here, listen to me. When it comes to here, those inputs, could they be of the same wavelength? They cannot be of the same wavelength. Why? Because this one is going to what? To combine them, to multiplex them. Are you following me or not? You cannot have what? The same wavelength here. How many modules do I need here? How many modules do I need here? A switch at what? At lambda 1. This one is a switch as what? At lambda, oh sorry, lambda n. I'm sorry, typo. Correct this one. N. A switch as lambda n. Okay, so individual wavelengths on a fiber. Individual wavelength. Now, is this, listen to me. What did I tell you about the matrix here? I told you about this routing matrix. It's what? It's fixed. In here, can you what? Can you adaptively change the switch connectivity? In other words, this lambda 1, where it is headed here, could it go this way? Here. Could it go this way? Here. It depends on what? How you are going to configure these switches. Did you get my point or not? Did you get my point or not? Where is the router, by the way? When I call it a router, where is the router? The router is the whole thing. This is the router. One more time. This is the router. An optical router. Clear? Clear? How many inputs does it have? It has n inputs. How many outputs does it have? N outputs. This wavelength here, lambda 1, could it go here? Could it go here? Could it go here? And does it adapt itself? You follow me or not? In other words, could the lambda 1 for the first time goes in here and then at some other time goes in here? It can do that. Are you following me? Because you are going to what? Configure the switch accordingly. Do you understand what do I mean by switch at lambda 1? Switch at lambda 1 means what? This one can only switch at what wavelength? At the wavelength of what? Lambda 1. There will be no other wavelengths on this switch. This is lambda 1. This is lambda 1. Is that okay, or is there a collision? There is a collision. Sorry, there is no collision. When will there be collision? Here. When will there be collision? There will be a collision if this lambda 1 is headed here and this lambda 1 is headed here. Did you get my point or not? Did you get this point or not? If both of these are headed to the same output fiber, then the switch cannot switch them both at the same time. There will be a need for what? Scheduling. Scheduling means what? Means that it needs to schedule which one will go through. And the other one will be what? Buffer. Clear? No response. Clear? Okay, good. So, individual wavelengths on a fiber can be directed to a different output ports. Routing matrix can be configured on what? On demand. When I say configured means what? You are configuring the what? The switching connectivity. Those are switching connectivity on demand. It still can support what? Can support how many connections? N square connection. Do you see why it is N square? We have N inputs and we have what? N outputs. Did you get this or not? Yes or no? Okay, good. Oh, this is an example of a what? A reconfigurable switch. This is a switch. Which state, by the way, how many states do you see here? How many states do you see here? 2 states. The bar state and the what? The QoS state. Let's see if you can help me here. How many inputs do we have? This is, again, this is this one. But with how many inputs? 2 inputs. Clear? So what do I have here? Lambda 1 A, lambda 2 A. This is the input fiber A. This one is what? Lambda 1 B, lambda 2 B. Clear? Could I have this situation? Let's see if you can help me. Could this one be a bar and this one be a what? A bar. What does it mean? A bar, a bar. What does it mean? This is lambda 1A. Yes? Where is it with? Mixed with who? Lambda 1B. So the output will be what? Lambda 1 A, lambda 1 B. This one will be what? Lambda 2 A, lambda 2 what? B. Did you get my point? Okay. Now, what is this? The first one is a what? Is what is this one? Okay. First of all, answer me the following question. Why is this one not allowed? Why is this? Do you see they're not allowed? Why? Because it's the same what? It's the same wavelength. Did you get it or not? Do you understand that this one is not allowed? Why? What is the input to this guy? What is the input to this guy? This is a multiplexer. What is the input to this guy? Lambda 1A, which means what? A wavelength lambda 1 carrying which information? A. And what is this? Lambda 1B, which means what? The same wavelength carrying different information. How is he going to combine them? They are the same wavelength. So this one is not allowed. Is this allowed? Do you understand, first of all, the notation? What does this notation means? Means this one is in a what? In a bar state. This one is in a what? Cross state. Let's see. What is this one? Lambda 1A. What is this one? This one is lambda 2B. Why? Because this one is in a cross state. Is that possible? That is possible. Why? Because this one is lambda 1, this one is what? Lambda 2. Here, this one will be what? Lambda 2, this one will be what? Lambda 1. How about the other way around? Is it possible? Cross and what? Bar. Yes? This one is also possible. Why is this one not allowed? This one is cross and this one is cross. Why is it not allowed? For the same reason. If this is cross, what does it mean? What do I have here? If this is cross, what do I have here? Lambda 2A, and what do I have here? Here, I have what? Lambda 2B, because this one is in a cross, which means what? The input to this multiplexer will be at the same what? At the same wavelength, but different what? Different information. They will collide with each other. Did you get my point or not? Did you understand it? So this one is what? Not allowed, allowed, allowed. This one is not allowed. Clear? Oh. Now, how about this? This is another device that we are going to be greatly interested in, which is called what? Optical add drop mux. Optical add drop mux. We call it what? OADM. OADM. Let's see if you can help me here. This is what? Lambda 1, lambda 2, all the way to lambda n. I'm going to what? I'm going to demultiplex them into what? Into lambda 1, lambda 2, all the way to what? Lambda n. Then what am I going to do with this? What am I going to do with the lambda 1? The lambda 1, I will what? Drop it. TE stands for what? Terminal equipment. I will what? Drop it here. And what am I going to add instead of it? Instead of it, what am I going to add? Another lambda 1, but carrying different what? Different information. From where? From where that information coming from? From this terminal. Where is this lambda 1 came from? Somewhere else. It came from somewhere else. It got dropped in here. This one will add what? A lambda 1 here. Same thing with this one. Same thing with this one. We call it a what? An optical add drop mux. Clear? Clear? So, by the way, each one of these is at the same what? Wavelength. You drop at what? One wavelength, and you add at a what? The same wavelength. Let me ask you a question. Here, did I drop what? Lambda 2. Yes? Could I add a lambda 1? Could I add a lambda 1 here instead of the lambda 2? Could I have added a lambda 1? No, I could not. Why? Because if you added a lambda 1, what will happen here? There will be collision. You will have a lambda 1 and you do have a lambda 1. Remember, this is a mux. What is the output here? The output is what? Is lambda 1 plus lambda 2 plus lambda n plus whatever, lambda 3 all the way to lambda n. Did you get this or not? Yes? Okay, good. This is called what? Optical added drop mux. Now, with the optical added drop mux, you could have what? You could have different topologies. So, for example, if you look at this one is called what? Optical added drop mux are used to retrieve or insert wavelength channels as a transit state. What do I have here? Lambda 1, lambda 2, lambda n. I drop what? I drop, for example, lambda 2, I add a what? Lambda 2. When I drop lambda 2, I need to what? I need to add a lambda 2, like I showed you in. So in here, this is what you have. It could also be a what? A ring topology, just like we saw in the case of Sonnet. Just like we saw in the case of Sonnet. So we do have what? Or ADM, or ADM, or ADM, or ADM. And again, each one of them can drop, add, and then what? Continue. Drop, add, then continue in a ring topology. Clear? In a ring topology, which consists of what? Multiple or ADMs. Now we will see shortly how we are going to what? How we are going to modulate all of these wavelengths in just a second. This is called a ring topology. This is called a what? A linear topology. Linear means what? Means on a straight path. This one is on a ring. So what do I have here? OLT stands for what? Optical line terminator. Optical. OLT stands for what? Optical line terminator. It goes through what? An OADM. Some wavelengths are dropped. Some wavelengths are added. Get multiplexed. Some wavelengths are dropped. Some wavelengths are added. Then what? OLT. Again, one more time. When I say dropped, where is it going to? It's going to an OLT here, in this location. OLT here, in this location, and so on. So, clear? Okay, clear? Most of the backbone, most of the core is of this variety, is of the ring variety here. Okay, now, this is the OADM before and after. The OADM before and after. We already discussed this earlier, but let's review it one more time. What is before? Before means what? Means that you need to what? Change it first of all to what? Electrical. So what do I have? I have a transponders, each at a certain wavelength. You are going to multiplex them. What do you need? In order to drop them, what do you need? You need to demultiplex all of them. Are you following me or not? Demultiplex all of them. Go through what? The re-amplifying, reshaping, and retiming. Drop some, add some, and then what? Multiplex again. And then what? Send it to this side. Did you get this or not? Yes or no? I want you to see this now. Look at what happened to here. This is now what? This is a 3-node linear network using what? OADM inside B. This one is what? It's a 3-node point-to-point wavelength division multiplexing before OADM became what? Became available. We had to what? Demultiplex all the what? All the channels, and then what? Drop some, and then what? Add some. Look at now what do we have? This is what? This is the multiplexer, several transponders. What am I doing here? I only want to drop, let's say I only want to drop lambda 4. What do? In here, I don't need a transponder. Did you get this here? I don't need these transponder. These have not been what? Dropped. The one that gets dropped, I need a what? A transponder. I drop it, and then what? I add it, and what? Put it a transponder, and then what? Multiplex it with this guy. These do not go through what? Do not go through this. Did you get my point or not? Did you get my point or not? In here, I needed to what? To demultiplex the whole thing, even though some of them are not going to be what? Dropped. Even though some of them are not going to be dropped, I still needed to what? To demultiplex all of them, and then what? Multiplex them again. In here, I don't need to do that. I just need to what? To drop the one that I need to drop, and then what? I add it together without changing any one of these. Clear? Clear? Okay. This is what is known as an optical cross-connect. They call it an optical cross-connect. OXCE. OXCE stands for what? Sorry, OXC stands for what? Optical cross-connect. It's not OCC. It's OXC. X means what? The cross. Optical cross-connect. Let's see how this one works. Several wavelengths in here, summations of what? Of all the lambdas, lambda 1, lambda 2, all the way. It gets what? Amplified. Demultiplex means what? Demultiplex means what? Lambda 1 plus lambda 2 all the way to what? Lambda 1 all the way to what? Lambda what? Lambda N. It gets filtered. This is a filter to ensure that only what? Lambda 1 coming here, lambda 1, lambda 1, lambda T, lambda N. And then what do I have here? I have a space switch. Remember, a space switch switches only what? In space. Tell me, where is this lambda 1 going? Can this lambda 1 goes in here? And through this switch, can this lambda 1 goes in here? And this lambda 1 goes in what? In here. Did you get this or not? Did you get this or not? And then on the other side, you do have a what? You do have a multiplexer and then what? Optical amplifier. Clear? So in here, this lambda 1 here could come in here. This lambda 1 could come here through what is known as a what? An optical cross-connect switch. Clear? Okay, good. Now, this is an example of an optical cross-connect 2 by 2. This is 2 lambda 1 and lambda 2. This lambda 1 here could come in here. This lambda 2 could come here. I showed you that a moment ago. Clear? Depends on what? Depends on the state. Which state is allowed or not. One more time. And remember, this lambda 1 and this cannot be what? Lambda 1 and lambda 1 both at the same time. There will be what? There will be collision in here. Okay. This is another example of an optical cross-connect. What do I have here? Lambda 1, lambda 2, lambda 3, lambda 4, lambda 1, lambda 3, lambda 4, lambda 4, lambda 3, lambda 2, lambda 1. Lambda 3 came here, here. This one, lambda 3 came what? Here, gets switched here, or it gets switched here, or it gets switched here, and so on and so forth. Clear? Clear? No response. Okay, good. This is also the cross-connect also, just like the OADM. It can be in a mesh type or it can be in a what? A ring type. What do we have here? Look at this. This is a ring that consists of all of these added drop mucks. And then I do have what? An optical cross-connect. Optical cross-connect means what? Some of them will come to this ring. Some of them will go to this ring. This is a what? Is a mesh type where you do have what? You do have several cross-connect, optical cross-connect connected in a what? In a mesh topology. Clear? These two topologies are the one that is most widely used in the core network currently. In the core network currently, either a what? A mesh topologies or a multiple ring topologies. Okay, this is a summary of the wavelength division multiplexing. Can you zoom in please a little bit? I just want to show you something. More. Thank you. What do you see? I want you to see outside of the network. You see all types of what? All types of services. For example, you will see a router in here. You will see an ATM network in here. You see the telephone network here, the PSTN. You see the what? SDH, digital cross connect, SDH, the synchronous digital hierarchy, or the SONET, ATM switch, all of these things. These are the what? These are the optical networks. This is the optical network. And they get what? All of these are what? Are the cross connect, all of these. Inside this network, they don't care about what? All of these what? Protocols. All of these protocols inside the network, you don't care about them. All what you care about them is what? Is inside the network is what? Is multiplexing the wavelength and transmitting the wavelength over what? Over optical connectivity. Clear? Clear? Okay. So, one more time. In the optical layer, which is what? Which is the wavelength division multiplication network design, realizing connections over what? Physical fibers using wavelength division multiplexing network element, OADMs or OXCE or OLT. One more time. OADM stands for what? Optical added drop mux. OXC stands for what? Optical cross connect switches. OLT stands for what? Optical line terminator. Clear? All of these are devices that are used in the physical or in the wavelength division multiplexing network. Now, for the most important part, which is the what? What do I mean by a light path? When you talk about light path, an optical connection assigned a distinct wavelength over a span of what? Fiber. Over a span of fibers. What does it mean when I say over a span of fibers? Over a span of fibers means what? There are multiple fibers. Are you following me on that? From one source to one destination, there is a span of fiber, and you do have what? Continuity of a wavelength. Continuity of a wavelength, which means what? Which means lambda 1 is available in all of these span of what? Fibers. We say we created a what? A line path. We created a line path. Let me see if you can help me here. Let me see, and we'll get to it next time. But let me just show you an example so that you understand what I'm talking about. Look at this and tell me, is there a light path between A and B? How many fibers does it go through? How many fibers does it go through? If you want to go from A to B, how many fibers? 3 fibers. Are you following me on that? If lambda 1 is available here, if lambda 1 is available here, if lambda 1 is available here, what do we say? We say that we do have a light path between what? A and B. Did you get this or not? Okay, now let me ask you a question. Could I have a light path at the same wavelength between C and F? At the same wavelength, could I have a light path? I could have a light path. Does this one interfere with this one? No, it does not. Why? Why? Because they do not span the same way. They don't go over the same way. Fiber. Listen to me. Can A connect to E via lambda 1? Can A connect to E via lambda 1? Can A connect to E? Can A reaches E via lambda 1? No, it cannot. Why? The lambda 1 here is already used. I'm not sure you are getting this point. Is the lambda 1 already used over this link? Over this fiber? You cannot use it again at lambda 1. There will be collision. Did you understand what I just said or not? Yes? Could A, listen to me, could A communicate with E using lambda 3? Making sure what? Lambda 3 is available here. Lambda 3 is available here. Lambda 3 is available here. And lambda 3 is available on this fiber. You created a what? A light path. Did you get this or not? A light path is a continuity of what? Of the same wavelength over a span of what? Over a span of fiber. Clear? We'll get to this shortly. I just wanted to explain to you what a light path is. Now, let's look at the network configurations. Different configurations for the wavelength division multiplexing. And this is what we are going to study for the next week or two. Broadcast and select network. Select and transmit network. Multi-hop optical networks with wavelength reuse, rearrangeable optical networks, wavelength routed optical networks, passive optical networks, FON, fiber to the home, FTTH, and then convertible wavelength networks. We will see all of these as we move along. Let's start with the broadcast and select. Let's see if you can help me. And see the diagram here and read the charts at the same time. An optical and select, a broadcast and select. What do I have here? Every device, every source, how many sources do we have here? How many sources do we have here? We have N sources. We have N sources. Every source, look at this here. A network that uses an optical star coupler which divides the incoming power. Remember, the star coupler, what does it do? It divides the incoming power from any sender equally among all outputs. Each access station, SI, has a laser which is a transmit light at a unique wavelength. So every device, every one of these stations can tune its transmitter. Can tune its transmitter to how many wavelengths? One wavelength. So this one can transmit at lambda 1. This one can transmit at lambda 2, lambda 3, lambda 4, lambda n. Are you following me or not? What is this one is going to do? This is the star coupler. What does it do? It will combine all of them and send it to what? To all the ports. Like I explained to you a moment ago when we were talking about the star coupler. One more time. What does the star coupler do? Let's get back to the star coupler. This is the star coupler. How many inputs do we have in this example? How many inputs? 4 inputs. At what wavelength? Lambda 1, lambda 2, lambda 3, lambda 4. Yes? How many outputs? 4 outputs. At what wavelengths? Lambda 1, lambda 2, lambda 3, lambda 4. Clear? Clear? Now listen to me. A broadcast and select. I want you to understand what do I mean by a broadcast. Each one of them is transmitting at a different what? Wavelength. What is the coupler is doing? What is the star coupler is doing? He is combining all the wavelengths and then what? Broadcast it to all of them. Did you get my point or not? Each station can be tuned to select what? To select one of these what? Wavelengths. What does it mean? Oh, I'm still not sure you are getting it. Every transmitter can transmit at only what? Wavelength, but it can receive how many wavelengths in this example? N wavelengths. In other words, the receiver is tunable, but the transmitter is what? It's not tunable. No, you are not getting this. I'm getting a little bit frustrated here. One more time. What is the broadcast and select? The broadcast and select. Every station has a transmitter and a what? Receiver. The transmitter is not tunable. What does it not tunable means? You can transmit only at what? One wavelength. Are you following? It's not tunable. But is the receiver tunable? The receiver is what? Is it tunable? You can what? You can tune your receiver to receive what? Any wavelength you want. So let's see if you can help me here. What is this one is sending? At what wavelength? Lambda 1, lambda 2, lambda 3, lambda 4, lambda n. Answer me the following question. Will there be collision? No, there won't be any collision. What is the star coupler will do? What is the star coupler will do? Will add them, combine them, and then what? Split them. Split the power equally and send it to who? To all of them. Now, if this one wants to send to this one, if this one wants to send an information to this one, tell me what is going to happen. Tell me what is going to happen. What is this? This one is the sender, this one is the receiver. Where is he going to put the information? He will put the information on lambda 1. What is this one is receiving? He is receiving lambda 1, lambda 2, lambda 3, and lambda n. All of them. Yes? What does he need to tune his receiver? He needs to tune his receiver to which wavelength? To lambda 1. And he will reject all of the other wavelengths and you tune his receiver to get what? To get only lambda 1. Did you get this or not? This is called what? A broadcast and select wavelength division multiplexing network. Before I let go of this, before we see what the problem here, do you understand what is the broadcast and select mean? Who is broadcasting? Is this broadcasting? This one is not a broadcasting. Who is the broadcasting? The star coupler is a broadcasting. The star coupler is combining all of these wavelengths, and then what? He is a broadcasting to all, and who is selecting? Each one of these stations, the receiver side. You tune your receiver to a certain wavelength, and you what? You select the channel that you want. Clear? Now, what is the problems? Let's see if you can tell me what is the problems. Question number 1. Will there be collision? There is no collision. So the collision is not the problem here. So what are the problems? Let's see. Tuning speed at the receiver. The receiver, a station needs some time to tune to a specific what? Wavelength. When you tune your receiver to a certain wavelength, you need some time. During that time, it cannot accept what? Packets. Why it cannot accept packets during that time? It's trying to tune to a certain what? Wavelength. Before you tune to a certain wavelength, all the packets will not be what? Will not be accepted. The tuning time should be small relative to the what? To the packet size. Do you understand what that means? Do you understand what that means? The tuning time needs to be what? Much shorter than the what? Than the packet transmission time. Clear? So that you can tune before the packet comes. Let's see if you can help me with an example. Let's assume you are transmitting ATM cells. ATM cells is what? Is 53 byte long. Okay. ACM cells are involved at a rate of what? OC12. What is OC12? It's 622.08 megabits per second. How long does it take to transmit the cell? How long does it take to transmit the cell? Can you tell me where this number came from? The 682. This is the cell transmission time. Where is this came from? Each cell is what? 53 times what? 8. Yes, bits. And I'm sending it at what rate? How do you calculate the transmission time? Transmission time is the length of the what? Of the packet. In this case, it's the length of the cell divided by what? The bit rate. The bit rate is what? 622.08 megabits per second. What do you get? You get this value. Which means what? What does it mean? It means the tuning has to be what? Less than that. The tuning has to be what? Has to take time, which is what? Less than 682 nanoseconds. Are you following me? Otherwise, this cell will be what? Will be lost. You are not going to be able to what? To read that cell, to receive that cell. That put a constraint on the tunable filters and also put a constraint on the number of stations that can be attached to the network. Why? Why? Why does it put a constraint on the number of what? On the number of stations that are attached to the network. Remember, every station attached to the network has to transmit at a different what? Different wavelengths. So if we do have, for example, in this case, let's assume we do have 250 stations. What does it mean? It means each receiver needs to what? Needs to be able to tune to how many wavelengths? 250 wavelengths. The more wavelengths you have, the longer it takes to tune to a certain wavelength. It's just like your radio. If you do have what? If you do have 100 channels, it will take longer to what? To tune on one channel rather than what? If you do have only 2 channels. Clear? So it puts a constraint on the what?
Professor, we have 5 minutes.
Thank you. Now, what is another problem? What is another problem? How does the receiver know to which wavelength it is what is supposed to tune to? How does he know? In other words, listen to the question first. This one is transmitting information to this one on which wavelength? Lambda 1. But how does this one know that this one is transmitting to it? How does SN know that S1 is sending something to it? S1 needs to first of all signal S2, SN, telling it what? I want to send some information to you. Did you get my point or not? So signaling. What is the signaling rate required to tell the receiver to which wavelength it should be what? Tuned to, and how to implement signaling. Let's take an example. Suppose the number of stations is what? Is 250. What do we need? We need, first of all, 8 bits to represent what? Or to identify these stations. Why? Why 8 bits? If we do have 250, each station needs to have an address. And how many bits do you need? You need 8 bits to represent what? To represent uniquely these 250 stations. 8 bits. Assume all the bits are sent to all the stations before every cell is transmitted. What does this mean? All 8 bits are sent to all stations before every cell is transmitted. Before this one is what? Before this one is transmitting, what does he do? He signals how many bits, using how many bits? 8 bits to all of them. To all of them.
The time is 21 o'clock.
Means something is coming on which wavelength? On a lambda 1 wavelength. Clear? So 8 bits. Now assume the ATM cells is at 622.08 megabits per second, which means that it roughly take what? This is what we calculated, 0.682 microsecond per cell. The signaling rate should be what? 8 times what? 250 divided by what? 0.682. Why? Can you explain to me where am I getting this? For every cell that you want to transmit, you need to send what? Signaling to tell the other that a cell is what? A cell is coming. Did you get my point or not? How many stations there are? 250. And how many bits are you sending? 8 bits to represent what? To represent the ID of a station. Yes? So it's 8 divided by what? 250. And you need to do that every what? Every 0.682 microsecond, because that is the cell transmission time. So it's 8 times 250 divided by what? 0.682. We end up with what? 2.9 gigabits per second. Only the signaling, which is not part of the information. Only the signaling is a rate of what? 2.9 gigabits per second. Now, actually, again, the signal rate will increase as a proportion to what? N log N. What is the N? N is the number of what? Stations. And log N is what? Is the number of bits needed to represent each station. Clear? Okay, so we do have a problem with this. The third problem is the following, with the broadcast and select. Suppose two stations have packets destined to the same destination station. Suppose two stations, in other words, we do have two stations, have packets destined to the same destination. This one is going to modulate the information over what? Lambda 1. This one is going to modulate the information, which is a different information on lambda 2. This one can tune his receiver to only what? One wavelength at a time, which means what? Which means what? We need to have a scheduler or a what? A controller and a queue to hold the packets or the what? The cells. Not sure, did you understand this? Did you understand this or not? Is it possible that this one and this one are sending to this one? This one is sending it at what wavelength? Lambda 1. This one at what wavelength? Lambda 2. Can this one to tune to two wavelengths at the same time? He cannot tune on the same wavelengths at the same time. Which means what? Inside this, we need to have what is known as a what? A scheduler or controller and queue to hold the packets ourselves. Packet cells also need to be synchronized so that they appear at the star coupler at the same time to get what? To get scheduled. Clear? It cannot be what? They need to be synchronized so that these star coupler can what? Can schedule them accordingly. Clear? Clear? Did you understand the broadcast and select? Now, next time, we will look at the next type, which is called what? Select and transmit. In a select and transmit, exactly the opposite as what? A broadcast and what? Select. In select and transmit, the transmitter is tunable, but the receiver is what? It's not tunable. In other words, the receiver can receive only at what? One wavelength, but the transmitter is tunable. You can transmit at what? At multiple wavelengths.
Professor?
Clear? In this case, could there be collision? Could there be collision? In other words, could this one and then this one transmit at lambda 1 and lambda 1? You didn't get it. Did you get it or not? The transmitter is tunable, but the receiver is what? It's not tunable. Could this one tune his transmitter to lambda 1 and this one is to lambda 1? Will there be collision? There will be collision. In here, there is no collision. In here, we need the scheduling. In there, we need the collision. We need solution for collision. But I think I ran out of time. Did I run out of time?
Yes, we are out of time.
We'll continue on this next time.
Okay, capture the ray and fade, please.
This concludes the 555 with Dr. Zahid. It's Tuesday, April 15, 2014.
The time is 22 o'clock.